Hello, my name is Eliza Simondera, and this is my lab report for the first lab, constant velocity. The purpose of this lab was to compare the observed and predicted position versus time graphs as a marker rolled along the floor. With that being said, the system was the marker and the surroundings were everything else, including gravity, friction, and air resistance. The laws that were applied in this lab were Newton's first law, which states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in a straight line, unless acted upon by an external force, and Newton's second law of motion, which states that the acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass. The equations used were Newton's second law, net F equals ma, the velocity update formula, and the position update formula. The experiment was set up by laying down a meter stick and setting the marker at one end. The meter stick is necessary for the tracking software, as it acts as a calibration stick. We then pushed the marker in a straight line, recording as it rolled along the meter stick. It was important to roll the marker in a straight line to ensure that it only moved along the x-axis. I then uploaded the video into the tracker software. Once it was calibrated and the axes were set up, I tracked its position frame by frame. This resulted in data that I graphed in Excel. I then used GlowScript to create the projected graph with the velocity and position update formulas. To analyze the results, I combined the two graphs and observed the differences. This is a video that we recorded of the marker rolling along the meter stick. This is a screenshot of the tracker software that we used to create the position versus time graph. As you can see, the meter stick is being used as a calibration stick, and the purple lines are the axes. The red diamonds following the marker's path are the position points. They were recorded frame by frame as the marker rolled along the video. As you can see on the right, the graph was made in the software and the data points are all below. After tracking the marker in the tracker software, I copied the data to Excel and created this graph. As you can see, the graph is not a straight line and instead has a curve to it. This is the GlowScript code. The highlighted boxes are lines that I changed. First, I set the mass to 0.0153 kilograms, as this is the mass of the marker. I then set the marker's initial position to 0. I found its initial velocity by finding the average velocity between the first two frames of the video. I set the initial time to 1.7 seconds, as this was when the marker was pushed in the video, and set the final time to 3.25, as this is when the video ends. I set the net force to be 0, as there was no acceleration on the marker. I added the velocity and position update formulas so that the position would update in each time step. I ran the code, and this was the model that was projected. The image on the left is the actual model of the marker rolling along the floor. The graph on the right is the projected position versus time graph. As you can see, this graph is linear and does not have a curve. When I combined the two graphs, I noticed that there was a large difference between the two models. By the end, the observed position is much lower than the predicted. This discrepancy can be noted to multiple things. First, there is friction from the floor. This friction would act on the marker, slowing it down. This was not accounted for in the GlowScript prediction. There was also probably human error in the experiment. First, the video was hand-tracked, which could lead to some errors in the position points. Another error is that we were unable to get the marker to roll straight. Every time we tried, it would veer off slightly. This is an issue because it is introducing another coordinate in the position that we did not account for. Our first discussion question is to determine what would happen if the axes were flipped. I believe that if the orientation was flipped and the positive x and negative x were interchanged, that the slope of the position versus time graph would be negative. Our second question is if it is possible to say how many pushes and pulls are being added to give a zero net force. I believe that there is no way to determine how many pushes and pulls are on the marker because there were forces like friction and air resistance. In a perfect setting, these forces would not exist and the net force would truly be zero. However, this was not the case in this experiment. Because of that, the net force wasn't actually zero, and this is why there is a lot of deviation in the observed graph.